Okay, we filmed almost this entire class. If 32 gigs is like close to 10 hours, yeah, then 1.5 divided by 10 times 32. This is 4.8 gigs of space, right? Compressed to something somewhat smaller. I get 2.9 times 10 to the minus 2. What units does magnetic field have? That's right. That's right. Yeah, you got it. I get like 100th. Oh, I got you with centimeters, didn't I? Yes, that's right. I get 0.029. So it's 0.17 meters is our length, yeah? Yeah, doggle hunt. Yeah, is that 0.029? Yeah. I love that. Yeah, that's right. So the question is, are they going to keep letting me upload videos day after day?
I don't see any reason why not. They won't stop it.
Somebody's got to make YouTube a lot more boring. I mean,
although YouTube, like, deleted my account.
There you go.
No reason.
Did they?
They deleted my account after I uploaded rap battles from last year. Which is funny because I think they probably deleted my account for copyright violations because we used the background music to song. But the people who didn't put this kind of song up there, they don't come to the main account.
Oh, so I wonder, maybe they'll find some nitpicky thing.
I don't see the copyright violations.
Yeah, I don't think so.
Unless you advertise.
Yeah.
You put like Avatar on it and watch it.
I think Google is one of the finest corporations.
Now the check is payable too.
There was a list of 8 reasons why Google is like God.
Yeah.
We've already taken over the world.
Number one, love them or new Google.
Careful. No, I'm just.
Rely on them.
Just submit to our all-powerful Google overlords. You can pray.
Okay, find the current. Okay, so this is supposed to be, nobody understands this, and this is perfectly understandable. So the force is 3.2 newtons. We've got a 3.2 newton mass. This is supposed to be a pulley, and it's trying to pull that thing out of the magnetic field, but the magnetic field is balancing it. So the force is 3.2 newtons. Then we've got a loop of wire, and the current is flowing in this wire. And the question is, let's see, find the current and its direction, right? So we can actually figure that out. Which way must the force be? If we're pulling this way and the magnetic field is exerting a force to counteract that, the force must be that way, correct? Now, there's lots of wire in the magnetic field here, okay? There's wire that goes this way, there's wire that goes this way, there's wire that goes this way. This is the piece of wire that makes the difference, okay? And I'll show you why that is in a second, but let's first presume that it's the direction of the force on this wire that is going to be the one that's important, okay? Now, we know that the force is to the left. We know that the magnetic field is out of the page. So therefore, the current on this part must be going down, yes? Okay, so the current on that part is going down, and so that means that the current is going anti-clockwise in general in that loop. Now, why doesn't this part matter? Well, there is a force on it. Let's figure out the force, okay? If it's going down here, then the current is going this way on this one, yes? Okay, so again, index fingers that way, yeah? Magnetic field out of the page. Which way is the force on this wire segment? Down the page, yes? Okay, which way is the force on this wire segment up there? Well, the current is flowing that way because it's in general going anti-clockwise, right? So the current flows that way. Magnetic field is out of the page. The force on this segment is up. That's interesting, isn't it? So if you take a loop and you have part of it out of the magnetic field, this part has no force on it, right? Okay, this part has no force on it, and this one's up, this one's down, but this one is to the left. In general, it's outward. It's trying to expand the loop. The loop will actually bend if it's flexible and try to get bigger, right? Okay, it's trying to expand the loop, but in general, the net force will be that way. And we've got two questions. Yes? How do we know to, say it again? How do we know to use the bottom wire? We actually use this wire as the important wire. Okay? How do we know? Because we know that the forces on these wires cancel each other out. Okay? So let's go through it again, right? The first thing we did was we said, okay, the force has to be down that wire to counteract this force. And we know that because magnetic field is out of the page, right? Okay? Current, and the force has to be, magnetic field is out of the page, force has to be that way, so my thumb has to be that way, right? Magnetic field's out of the page, current has to go down in that stretch of wire, yes? To generate a force that way. Right? These wires, by the way, could not generate a force that way or this way. They could only generate a force that way or this way, right? Because of the whole right-hand rule thing. So if the current's going down in this stretch of the wire, that means it's going this way on this part and that way in that part, which means they have to be in equal and opposite directions, right? Equal forces in opposite directions. And in general, this force right here is going to be current that way, magnetic field that way, down. This force on this one with the current going that way is current this way, magnetic field that way. It's going to be up, right? What if we put the whole loop in the magnetic field and the magnetic field was uniform? What do you predict? They would all cancel each other out. This would be up, this would be down, that would be to the left, and this one would be to the right. The loop would be trying to get bigger, but it can't get bigger, right? And so there'd be no net force on that loop, okay? But yeah, now what if this thing though was, yeah, that's interesting, right? But it might not be stable, right? This loop would actually want to orient itself so that it was facing the direction of this magnetic field, and we'll talk about that later. We've got answers. Yes, and anti-clockwise is what we got it. So people are now getting the numeric answer to this. If we put that loop inside the magnetic field, would it be stable? There'd be no net translation force, but there might be actually a tendency for it to twist if it got slightly off kilter. Yeah. Yeah, that's right. So how would you know whether it was stable or not? That's right. In other words, I can get a North Pole magnet and face it with another North Pole magnet. And if I make this North Pole magnet and this North Pole magnet point exactly toward each other, they'll balance, won't they? Yeah? But if it slightly gets to the side, it'll spin around, yeah? Like that, yeah? But there is a stability, right, where it's like this, where it will just stay, yes? Okay, so the question is, that loop with wire going in it is a magnet. Is it stable? Anybody have an idea? Yeah, that's right. Well, which way, didn't we say that it's going anti-clockwise? Which way is the North Pole? Well, the North Pole is the side facing you, yes? Okay. Now, this magnetic field here, where's its North Pole? Well, this is hard to, let's think it through, right? Don't field lines go out of North Poles? Yeah? So the North Pole is behind the page, yeah? Right, because the magnetic field's coming out of it, right? So the North Pole is behind the page. This loop is like a magnet. Where's its North Pole? Isn't it away from behind the page? Isn't the South Pole of that little loop toward the North Pole that's behind the page? So is that stable? Yeah, it's stable, right? Yeah, it would be happy. It would just sit there and go.
So if the current's traveling clockwise,
if it was going clockwise, it'd have its North Pole facing that North Pole behind the screen. And although it would be, technically, if it was in the plane of the page, zero net force, as soon as it got slightly to the side, it would pivot around, just like the little pivot there. Huh? Well, this was my goal as a kid, right? Was that I would put ceramic magnets in a room, pave a room with North Pole magnets facing up, yeah? And then I would make a skateboard with North Pole facing down on the skateboard.